Alright, this is going to be the last video that's going to deal with the Fourier series for this class. So I want to write one thing on the board and then we'll get started. If we have y of t is equal to the summation from k is equal to negative infinity to infinity h of j omega naught k times a of k exponential e to the j omega naught kt. Change the markers. The terminology that's used in this book for this in our text is the summation from k is equal to negative infinity of b of k of the exponential of j omega naught kt. So this b term is what they're using to call the output of the A through the system H. So, alright, so keep this in mind. This is terminology that's used in this text. So here are some of the properties of the Fourier series. Fourier series. Number one is linearity. If we have y of t is equal to a of x of t plus b of omega or w of t, then it has a period both if x of t and w of t have omega naught as the fundamental period. Then we can come up with coefficients c of k, which are going to be equal to a, which is a constant, times the a of k, plus b, which is the constant, and b of k. This b is not that b. The notation is oftentimes confusing. All this is showing is that if you determine the Fourier series coefficients for this guy, and they have the same fundamental frequency, you can scale them and add them to find new Fourier series coefficients, c of k, that describe y of k. Alright, 2. Scaling and offset. So, if we say y of t is equal to a x of t plus c. What is this? C is a DC offset. Alright, this is a special case. So, the Fourier series are 0 for k is not equal to 0, but b for this guy. So, coefficients are 0. Are 0. For k is not equal to 0. So, this doesn't have any frequency content except at k is equal to 0, the coefficient, and for this guy we're going to use this notation, So b of 0 is equal to c. So this b of 0 is applying that DC offset to this entire term. So we can use linearity to say, if we have a DC offset, that's that b of 0 term that can be applied here, and it can be added to the a of 0 term here to obtain the final y output term. So what I just said there, so c of k which c of k is the Fourier series coefficients for y of t, and this is what they use in the book to define the output of this. And I wrote that up here so that you would know these coefficient terms, they rename them all the time. So if you see a new label for it, try not to get confused. Look at where it's being derived from. So down here, we're saying that this c of k describes the y of t. Down here, c of k is describing the y of t. So c of k is equal to a of k, or a times little a of k, for k not equal to 0. And c of 0 is equal to a of 0 plus c for k is equal to 0. When we have a DC offset that's applied to the system, that just adds the DC offset to the DC component of the output. All the others remain the same. Now this is a very important thing to remember, and it's not explained well here, but think back a little bit when we were talking about the definition of a linear time invariant system. If it has a DC offset, is it linear time invariant? No. So what we have to do to analyze these things is remove the DC content out of it, analyze it, and then put it back in on the end. That's what this is saying we can do. We can take this DC content, which is C0, and because of the linearity property, we can remove it. And it doesn't affect any of the analysis. We can work it through the system, and then at the very end, we just put that DC content back in, and we're good to go. So, all that saying, if you have a DC offset, you can do the analysis for all of these things with it removed, and then add it back in the end. Alright, property number 3, the time shift. Okay, y of t is equal to x of t minus t naught, time shift. But it also has a period of t naught. Keep that in consideration. So, this show, okay, it also has a period of t naught and its Fourier coefficients, c of k. So the Fourier coefficients are equal to a of k, exponential of negative j, k, omega naught, t naught. And let's call this td instead of t naught. T delay, because t naught is defining the fundamental period. So TD is the delay, T naught is the fundamental period. So just keep in mind this is the delay. So if we have a time shift, that's reflected in the coefficients by taking the coefficients that you can find and just shifting them by this. So if you have a function that looks even, but it's been time shifted, the property that we talked about earlier, where it's all real or all imaginary, is no longer true unless it's centered about the origin. So if you do have a signal that's time shifted away from the origin, you can use this property to time shift it back to the origin, find all the A of k values, and then apply this e to the negative j to it to put them back out there in time where they need to be to do the analysis. Alright, 4. Time reversal. A flip. Alright. So if x of t is real, y of t is equal to, let me write this down here, y of t is equal to x of negative t. Alright, so we've got our time flip. The coefficients, c of k, are equal to a complex conjugate of k. This is if x of t is real. If it's not real, remember back to that other video that I showed where we had the coil of yellow representing the signal running through space. And when we flip time, if it's imaginary, it inverses the imaginary also. So there's additional things you need to do if this is imaginary. Okay, but let's look at this one just a little bit more. I think I have enough room over here to do it. No, I'm just going to erase this. So, let's look at this real quick. C of k is equal to, I'm going to erase this just so I don't get confused. C of k is equal to 1 over t naught of the integral over the period of t naught, x of negative t, e to the negative j, k omega naught t, dt. And let's make a substitution into x of t, x of tau for e to the j k omega naught tau, negative d tau. And the substitution that we make is that tau is equal to negative t. So we took this guy and we just substituted in the negative t all through there, and this is what we get out. And then we can say 1, 4, and then this is over t naught, x of tau, exponential of negative j k omega naught tau plus, oh shoot, sorry, I skipped the line.